Welcome back. So this is the last talk of the day, the last talk of the week, and the last talk of the whole program. Though it's the last one, but he will present his latest results. Suneel is a postdoc at IISER Tirupati, and he did his PhD from IISER Mohali with Abhi Ganguly, and he will be speaking on the local constancy of set and mod P Galois representation. The floor is yours.
Thank you, sir, for introduction. And first of all, I would like to thank the organizer for giving this opportunity. And secondly, this is my joint work with my PhD advisor, Dr. Abhi Ganguly. And I'll be talking on local constancy of certain mod P Galois representations. So let me start with the introduction. We assume P Vn odd prime and F Va normalized cuspidal eigenform of weight k greater than equals to 1, character psi, and level gamma 1n, such that P is away from n. We note that F being an eigenform, it means that it is an eigenfunction for all the Hecke operator Tn, with the eigenvalues given by An, the Fourier coefficient of F. And the work of Delin, Delinscher, and Eckler-Shimura associates to F a two-dimensional periodic Galois representation, rho F, such that rho F is unramified at all the primes L away from P and N. Here unramified means when we restrict rho F to the inertia group at prime L, it is unramified. And being unramified, so it makes sense to that rho F restricted to Froebel. Here Froebel is the Frobenius at prime L. And the characteristic polynomial is given by this polynomial. Here AL is the TL eigenvalue of F. By local structure of rho F at prime L, we mean that rho F restricted to GL, where GL is the absolute Galois group of QL and identified as the decomposition subgroup of absolute Galois group of Q at prime L. We note that the local structure of rho F at prime L is when L is away from P and N is completely determined by this triplet AL, K, and psi, as the characteristic polynomial of Froebel, rho F at Froebel, is determined by this triplet. And now we would like to discuss the local structure at prime L equal to P. And we ask the same question, is it completely determined by similar triplet? And we will come to this question later. Let me first give some classical result in this case. In the ordinary case, meaning when AP is periodic unit, a result of Delin determines the mod P reduction of rho F restricted to GP up to semi-simplification for all the weights k greater than equals to 2. In the non-ordinary case, meaning when AP is not a periodic unit, Fontaine and Addix-Owen determines rho F bar at inertia at prime P for all weight lie between 2 to P plus 1. And we note that in this case, L equals to P, rho F restricted to GP is ramified, unlike the case L not equal to P, where it was unramified. Later, result of faultings proved that rho F restricted to GP is a crystalline representation with Hofstadter weights 0 and k minus 1. Now I would like to discuss more about this crystalline representation. Colmage and Fontaine studied the crystalline representation in terms of some semilinear objects, precisely in terms of weakly adversely filtered phi module. They proved that the Funter decrease defined as this is an equivalence of the categories. From the category of crystalline representation of GP over QP to the category of weakly admissible filtered phi module over QP. Now let me take an object in this category. For an integer k greater than equals to 2, and AP is a non-zero element of QP bar with positive valuation. Let DKAP be the weakly admissible filtered phi module of Sol of dimension 2. Since decrease is an equivalence of the category, so there existed two-dimensional crystalline representation BKAP. of GP such that decrease of BKAP dual is isomorphic to DKAP. And we note that DKAP does not have sub-object in the category of weakly admissible filtered phi module. And hence, the representation BKAP is an irreducible crystalline representation with hosted weights 0 and k minus 1. And the characteristic polynomial of Frobenius phi is given by this polynomial. We note that up to an unramified twist, rho f restricted to GP is isomorphic to BKAP. And we note that we also note that this BKAP is completely determined by K and AP, as DKAP is completely determined by K and AP. And hence, the local structure of rho f at prime P is determined by this triplet. And we are interested in the basically mod P reduction of Galois representations coming from the weakly admissible filtered phi module. And okay, let B var KAP be the mod P reduction of a G stable lattice of BKAP up to semi-simplification. And so it is independent of the choice of GP stable lattice. We can see this using Brownian-Schmidt theorem. And we note that B var KP has been studied by for various weights and slope ranges. And here we mention some of the results computing explicitly B var K prime AP. And it has been computed for the following range of weights and slopes. For all the slopes, positive and weight lie between 2 to 2p plus 1, it is due to Broglie. And for all the basically all the slope greater than equals to k minus 2p minus 1, it is due to Verze, Lizou. And then recently the bound this k minus 2 to p minus divided by p minus 1 has been improved to k minus 1 divided by p by Bergdahl-Levin. And for all the slope lie between open interval 0, 1, it is due to Vazard and G. And for all slope basically closed interval 1 comma open 2, it has been done in many papers, basically Ganguly Ghate, Bhattacharya Ghate, and Bhattacharya Ghate, Rosenstein, and Ghate Rai. And the Ghate Bangla and Chitra Ghate Yashoda, these papers can be also seen as related to local constancy. We basically consider a slightly variant of the question computing B var KP for all weights. And let me explain what I mean by variant. So as we noted that VKP is completely determined by AP and weight K, and so is V var KP. So by fixing AP, we define a map, K goes to V var KP on the weight space. We study the question of local constancy of this map. In general, local constancy may not exist for given values of K and AP in the world of crystalline representation. The zigzag conjecture of Ghate provides an important counterexample of local constancy when weight K equals to 2 nu AP plus 2. And here nu AP is half integral. Okay, so before we discuss some counterexample arising from zigzag conjecture, let me quickly define some notation. We fix a fundamental character omega 2 of inertia subgroup IP at prime P of level 2. And for a non-negative integer such that P plus 1 does not divide A. The representation int omega to the power A denotes the unique two-dimensional irreducible representation of GP, such that its restriction to inertia is reducible and isomorphic to omega to the power A, direction omega to the power AP. And the determinant character is given by omega to the power A, where omega is the mod P reduction of p-adic cyclotomic character. Now let me discuss a counterexample of local constancy. We take k equals to 5, p greater than 7, and AP equals to 3 by 2. We note that valuation of AP is 3 by 2. And so we are in the situation k equals to 2 nu AP plus 2, basically in the territory of zigzag conjecture. And we consider here this disk in the weight space of radius p to the power minus t and with the center k. We use a result of Broglie to compute reduction at the center. and it gives B bar Kp is isomorphic to int omega to the power 4. And to compute the reduction in the puncture disk, we use a result of Ghater, basically zigzag conjecture for slope 3/2. And it gives that B bar K prime AP is isomorphic to int omega to the power P plus 3. Here K prime is coming from the puncture disk of this. And we note that the representation int omega to the power P plus 3 is not isomorphic to int omega to the power 4, as they do not agree at the inertia group. And hence we get that local constancy does not exist K equals to 5 for and AP equals to P to the power 3/2. Now let me give an example. In this example, we just change AP by a periodic unit, and all other parameters are just same as in the previous counter example. And so we are still in the situation K equals to 2 nu AP plus 2, basically in the territory of zigzag conjecture. And we use the same results to compute the reductions here. And it gives that in the interior disk, B bar K prime AP is constant and isomorphic to int omega to the power 4, which is irreducible representation. And in this annulus, B bar K double prime AP is reducible. And hence we get, and this interior disk is of radius basically P to the power minus 2. So we get this interior disk is the largest disk in the weight space around K, on which B bar K prime AP is constant. And hence we get the P to the power minus 2 is the radius of local constancy for K equals to 5 and AP equals to this value. Now let me give results which shows the existence of local constancy. The first results proving the existence of local constancy is due to Verze. He proved the following result. Suppose AP is non-zero with positive valuation, and also suppose that K and slope, weight K and slope satisfy this relation, then there exists a constant M depending on K and AP such that B bar K prime AP is constant in this disk as a function of K prime. Okay, so in this theorem, we note that this theorem does not give any explicit bound on MKP, and also does not determine the structure of B bar Kp in the disk of local constancy. Bhattacharya gives the first explicit bound, upper bound on MKP for small weights by computing B bar K prime AP explicitly, where K is strictly greater than 2 VAP plus 2. We note that this is just outside the territory of zigzag conjecture. And she precisely proved the following result. The content of this result is that suppose K is B plus C times P minus 1 plus 2, and slope lie in the range C to P by 2 plus C. And if K is greater than 2 VAP plus 2, then Verger constant MKP exists and bounded above by 2 nu AP plus 1. And the fact that this result is only for small weights directly coming from the fact that C is bounded above by 3 and B lie between 2 to P minus 1. Here this bound condition B greater than equals to 2C and the upper bound on slope is a bit technical, but the lower bound on the slope is more conceptual, and we will come to this later. Our main result basically answers the question, what happens to the local constancy when C is greater than equals to 4 or B is less than equals to 2C minus 1. Before we state our main result, let me give our key ideas to prove local constancy. We note that Bhattacharya's and our key idea to prove local constancy are same. And we basically what we do is we consider a disk around K of radius P to the power minus T in the weight space. And then we show that in this puncture disk, B bar K prime AP is constant as a function of K for some T greater than equals to T naught by explicitly computing B bar K prime AP. This gives the local constancy in the puncture disk around K in the weight space. And next, we determine the structure of B bar K AP at the center by either applying Verger's local constancy theorem or the following result of Verger-Liju to establish local constancy in the whole disk. Now let me state a result of Verger-Liju. It says that if slope is strictly greater than the ceiling floor of k minus 2 divided by p minus 1, then it gives b var k prime ap explicitly. And we note that here b var k prime ap is irreducible if and only if p plus 1 does not divide k minus 1. Now we fix some notation. In our main theorem, k denotes the b plus c times p minus 1 plus 2, with v lie between 2 to p, c lie between 0 to p minus 2, and p is greater than equals to 7. And we note that if we write k in this form, then this lower bound on slope in the result of Verger-Liju. Generically, it is c, and this is the reason why slope greater than c condition occurs in the result of Bhattacharya and also in our result. So we basically prove the following result. For fixed AP such that slope lie in this given range and k is greater than 2bap plus 2, then outside this finite sporadic set E, b var k prime ap is constant on this disk, where t is bigger than equals to 2 nu ap plus epsilon. The set E in this theorem is basically is a finite set and given by the k congruent to 1 comma 3 mod p plus 1. Now we will make some comment in the context of this theorem. The above theorem shows that Verger constant mkp exists and bounded above by twice of ceiling function of twice nu ap plus epsilon plus 1, and the set E in the theorem is given by this set. The ordered pair V comma C in E are those points for which b var k prime ap may possibly be reducible. If local constancy exists for k, then using a result of Verger-Liju, we get that b var k prime ap will always be reducible if k is congruent to 1 mod p plus 1, and it will be irreducible in all other cases. Now let me explain how we use mod p local Lagrange correspondence to compute b var k prime ap. So for that, let me briefly explain what mod p local Lagrange correspondence is. So it is an injection from the set of semi-simple two-dimensional fp bar representation of absolute Galois group of qp to the semi-simple finite length smooth admissible fp bar representation of GL2QP. Here we note that this GL2 representations of GL2QP on this side are infinite dimensional. And here by smooth representation, we mean that stabilizer of each vector each vector of the representation is an open subgroup of GL2QP. And by admissibility, we mean that its invariant space under every compact open subgroup of GL2QP are the finite dimensional. And we also note that both these sides of mod p local Lagrange are given very explicitly, which is important as in the computation of b var k prime ap. But we will not give explicitly, but let me give the what I mean by the compatibility of periodic and mod p local Lagrange correspondence. So let me explain this compatibility of periodic and mod p local Lagrange using this diagram. In this diagram, the top arrow shows the periodic local Lagrange correspondence, which associates to each crystalline representation of GP a Banach space representation of G. Here G is the group GL2QP. And the bottom arrow denotes the mod p local Lagrange correspondence, which we have just seen. And the vertical arrows are showing the mod p reduction. By compatibility of periodic and mod p local Lagrange correspondence, we mean that this diagram is commutative. And now let me explain how this compatibility of periodic and mod p local Lagrange correspondence allow Breuil to give explicit methods to compute B var K prime AP. So Breuil explicitly constructed a locally algebraic representation pi K prime AP of G with a G stable lattice theta K prime AP, such that certain completion of this pi K prime AP under some unitary norm is isomorphic to B K prime AP. And the mod P reduction of theta K prime AP is isomorphic to the mod P local length image of B K prime AP, basically this isomorphism. And we also note that mod P local length is an injection. So to compute B var K prime AP, it is enough to compute theta var K prime AP. And now let me explain our key idea to determine theta var K prime AP. We write R equals to K prime minus 2 and let BR be the symmetric power representation of GL2FP. Here GL2FP act on BR by the homogeneous substitution. And now let theta var with the polynomial of degree p plus 1, precisely x to the power py minus xy to the power p. And we note that GL2FP act on theta via the determinant character. And for m belongs to n, we denote BRM by the all those polynomials of BR which are divisible by theta to the power m in this ring. Since GL2FP act on theta via the determinant character, so this BRM subspace becomes the sub-representation of BR. And then using a result of buzzard G, we get the following surjection. Here int kzg denotes the compact induction, basically a space of all the locally constant function from G to this space which are compactly supported, and also satisfy kz linearity. Here k denotes the GL2 GP and Z denote the center of GL2QP. And the action on this space is given by the right translation of GL2QP. So now let me consider a filtration on this space. Sorry. Oh yes. Here nu denotes the basically floor of slope. Yeah. New floor of new AP. Yes. Okay. Precisely, we consider the following filtration, and we note that this compact induction is an exact functor, and so the successive quotient of this filtration are isomorphic to int kzg BRM modulo VRM plus 1 for m lie between 0 to nu. In order to determine theta var K prime AP, what we do is that under the hypothesis, our main result, we prove that the map P surjects from one of the successive quotient, precisely m equals to c minus epsilon. Here epsilon is a technical constant depending, basically lie between 0, 1, 2, depending on some B and C relation. And we basically get this surjection. P from this theta, from this quotient to theta K prime AP tensor with FP var. And to compute theta var K prime AP, we use again a result of buzzard G from the same paper. Basically a slight variant of that result gives us theta var K prime AP. And so that's all I wanted to say. Here are some references.
Yeah, are there any questions or comments?
Yes, this is probably a very naive question, but when you showed the disks at the beginning for counterexamples of local constancy,
yes.
So the two behaviors, like we have a disk and in the middle, the
maybe I can go
changes. and the other one is an annulus, and then a disk where it's constant. All these behave. Do we know if it's the only two possibilities, or could there be anything more?
Sorry, should I go to the?
Yeah, with the draw, with the disks. Yes, and this and the previous one, it suggests some sort of I don't know, semi-continuity or something. Do we know if it's
here reductions are already basically we know by the result of Ghaterai. Explicitly we know, and also at the center. So basically Breuil and Ghaterai result, using that we explicitly know reduction for all weights, and we get that this map is just constant on this interior disk, but it is not. Basically, whenever we take the bigger disk to this, we will not get the map is not constant.
Okay, maybe for the previous one as well, the previous slide. So when we do not have a small disk where it's constant, is it the only possibility that we get outside the center? It's constant locally, and in the center it's different. Or could something else happen?
Okay, so for AP equals to this, we are getting exactly this outside the center. Everything is just constant for t greater than equals to 1. But at center, it is not matching.
Yeah, I mean, is this the only thing that can happen in general, or general K and AP?
In general, actually, I don't know.
Okay,
maybe. Yeah.
Yeah, are there any other questions?
So this is also a very naive question from someone who doesn't know anything about this. I wanted to ask about the behavior. So here the representation, the reduced representation jumps from omega 2 to the 4 to omega 2 power p plus 3. And the difference is p minus 1.
Sorry?
So if I look at these two reduced representations, right, I have omega 2 power 4 and omega 2 power p plus 3. And the difference in the exponents is p minus 1.
Yes.
This sounds like an important number. There's some sort of general explanation for why the exponent would jump exactly by p minus 1?
General, I don't know, but here the reductions are, I just know that reduction basically is isomorphic to this and this. So I don't know why this p minus 2 is coming.
Thank you.
Yeah, any more questions? No, I just have a question. So why do you do it range by range? Like 0, 1, 2, 3, etc., and then half 3 by 2. So what is fundamentally the problem when you want to do it for a general case?
Okay, so these are the basically results which computes this. Basically, we are interested. Basically, these results are in the context of computing V var K prime AP explicitly. But in general, computing this V var K prime AP is really hard. So the first result, basically, there are two types of result for all slopes, but we have bound on the weights. But then these are also these results giving the slope, but slope is anything, but we get the bound on weights. But in the Wizard G result, there the computation becomes hard to like this explicitly computing V var K prime AP. So people are working this by region like slope lie between 0 to 1, and then for basically for these papers gives the reduction in these cases.
Maybe just one more question. So what kind of implications you have if you know local constancy?
If I know the
local constancy,
yes.
Like what kind of implications does it say modular forms or anything that you want to see? Like fine, I know something local constancy holds. You try to see the range, but what are its implications?
So basically, if we have the local constancy, then we I mean we know the structure of V var K prime AP in this.
Yeah, that is true. But how do you use that fact? That locally they are the same.
Sorry?
You know that locally it's constant, you know the structure of AP, so how do you use it in some context?
So I don't know the application of that, but we just study the local constancy.
Yeah, I don't mean to rocket science, maybe somewhere in the middle. Okay, fine. Yeah, thank you. If no further questions, yeah, let's thank the speaker once again.